All right. Howdy, howdy. Good morning, good afternoon, and good evening, depending on where you are attending this webinar from today. I hope you are having an absolutely lovely day. I know I am, and it's only going to get better in the next few minutes here. My name is Tim Sylvia. I'm an editor with PV Magazine USA, and I will be your moderator for today's webinar, Are You Tracking or Stowing? A financial analysis of stow strategies. But I will not be alone today because joining me are two top-notch, top-tier, excellent presenters. Pedro Magales, the Global Director of Engineering and Research and Development at Arctech Solar, and Cesar Higuedalo Lopez, a Principal Engineer and Tracker Expert from DNV. Right before we hop into these two presentations, I just want to take a couple of minutes of your time to get some housekeeping out of the way. This webinar will consist of a brief presentation with an audience Q&A session at the end, though you are free to submit your questions at any time during the presentations, and it is encouraged that you submit your questions as you have them and do not hold them. Due to time constraints, we may not have time to address every single question, but we will certainly make our best attempt to, and we can send especially pressing questions that were not answered to our presenters after the webinar in an attempt to get feedback on what you would like to know most about. If you have any technical difficulties during this webinar, the easiest way to get rid of them, it even works for us as presenters, is to refresh the webpage. If that doesn't work for whatever reason and these problems persist, shoot us a message and we will work to resolve it for you. In addition to myself, my colleague Beatriz is waiting in the wings to assist with any potential difficulties. Okay, now that all the housekeeping is taken care of, let's switch our focus back to the topic at hand. Optimal tracker stow strategy, say that 3 times fast, especially in the face of extreme wind and minimizing production losses and maximizing the financials of a project by keeping it out and generating until the last possible minute, safely, of course. Developers shopping for single-axis trackers are likely to look for a model that can withstand very high wind loads, but these reasonable safety concerns should be considered with the project's economics in mind. Current large format PV module trackers already move into stow position at lower and lower speed thresholds, which means they could be in stow very often, defeating the very purpose of a tracker. As a solution, Arctech has proposed raising the wind speed threshold that triggers stow position, a decision which would greatly decrease production losses, but ultimately seems, at least to an outsider, that it could add to even greater losses in the event of module failure or any sort of disruption caused by that very, very high wind on a solar array, which is essentially a sail. But as an outsider, I'm not the one presenting, and this is Arctech's hypothesis, so why not let Arctech expunge on it? So to better understand what went into the development of the hypothesis, the financials behind the reasoning, and all sorts of other information, I'm going to now turn it over to the first of our presenters, Pedro. Pedro, thank you for joining us today, and the floor is yours once you would like it.
All right. Thank you very much, Tim, for the kind introduction. We have done this, we talked about this topic a few months ago, I think in December, in a PV Magazine webinar. So I'm just going to refresh the audience's mind here about the topic of stiff trackers. Back in December, I said stiff trackers are the future of PV plants. They're not really the future. They are really the present, the most current, and they should be the state of the art that everybody in the tracker business moves towards. Okay. What is a stiff tracker? A stiff tracker is a tracker, well, as its name says, with a higher rigidity when compared to the traditional flexible trackers. We all have in mind those single degree of freedom systems that when the wind comes move quite significantly. So stiff trackers actually constrain that movement and allow for minimal deflection of those PV panels. And for the first time, they enable a stow position, flat, facing zenith, what we call it 0 degrees here. Okay, and this is very important, and it's very important because if we look at these slides, I presented these animations last December. If you're looking at the top video here, this is a wind tunnel test that we have done at our partners, CVP Wind Engineers, and here we are testing our traditional flexible tracker. You can see, I'm going to stop this video for a little bit. You can see here that there's only a single fixed point right there, and then the wind is coming from the left. Okay, and then when the wind hits these trackers, they almost all behave differently. Okay, this is a characteristic of having flexible trackers in your plants. So the wind is coming from the left. For instance, let's take a look at the first tracker. Around the fixed point, this tracker keeps its original tilt, its original position. But as you move along farther away from the fixed point, this set of modules right here is almost vertical. The second tracker, though, keeps its original tilt throughout. And then the other trackers start oscillating. Just take a look at the video one more time. And you can see that at some point, like these interior trackers here go completely crazy, right? So you can see this super movement here. This means like panels flying away and torque tubes getting torsioned and posts bending and everything, okay? Now, the difference when you actually test stiff trackers is that, one, they all behave like the same, as you can see. So the wind is coming from the left of your screen right here. And you can see that the behavior is very similar in exterior trackers and interior trackers. And more importantly, we have more variables to play with. These trackers right here have two fixed points, where my hand is pointing to, right there and right there. So we define two different spans, what we call the fixed-to-fixed span and the fixed-to-free span. And this allows us to optimize these lengths so we have more or less movement in these two independent spans. It also allows us to put, more fixed points or to move the location of those fixed points. In essence, it allows us to configure the best system for any given project. Just two more notes on this one, because I presented all these in previous webinars. If you guys are curious, just have to reach out to me, and we can take a deeper dive on this one. But basically, it's important. Let me just stop this. It's distracting. If you compare these two maps, these are the stability maps for the traditional flexible tracker, and the stability map for a rigid tracker. And what you can see right here is that the worst ever position for a traditional flexible tracker is when the tracker is flat. You can see the lowest critical wind speed. Critical wind speed is the wind speed upon which the tracker starts deflecting too much, okay? So the worst tilt is around 0 degrees, okay? On the other hand, the best tilt here is around 0 degrees, okay? So you can see that by just rigidifying the tracker, the dynamic behavior changes completely. I'll come back to this later. A few numbers for you. So, these are typical numbers of all traditional trackers in the industry right now. By the way, this was our old Skyline tracker. It was very typical to mount this Skyline tracker in a 3-string configuration. So you used to have like a 100-meter tracker with a fixed point in the middle. So kind of like a 50-meter wingspan on either side. And those trackers must stow at a steep angle, either 30 degrees or 45 degrees, as you can see here. Because if you stow those trackers at a flat angle, you cannot go beyond than around 20 meters per second. And guess what? You have 20 meters per second several times a year. So if you were to stow these trackers flat, these trackers would basically get, they would basically fly away. Okay? Now, instead, these trackers right here that are very rigid, for starters, their minimum critical wind speed is larger. So we went from a minimum in the 20s to a minimum in the high 30s. And then the location of the minimum is different. The minimum here used to be at 0, like I said before. And the minimum here in this one is at steeper tilts. Now, just one more note, and without getting into heavy physics here, but what drives this effect is basically stiffness. And what drives the critical wind speed at steeper tilts is more damping ratio. So these trackers right here have just one fixed point, one slew drive in our case, and then plenty of dampers along the torque tube. As a matter of fact, we use up to 6 dampers in the exterior rows and up to 4 dampers in the interior rows. Here, we have more slew drives, more fixed points, no dampers whatsoever. And that's why you observe these small drops right there. Because if we were to put more dampers, this would likely be a flat line. Okay? Well, anyways, moving on. So, why should we use rigid trackers today in 2022? Like I said, because we have the highest stability at all tilts, and because it protects the panels. And we're going to talk about the panels a little bit, but if you remember, the panels used to be, a 2 square meter surface, 2 meters by 1 meter, and today panels go up to 2.4 by 1.3. That is 56% more surface, which means that, when the wind comes, the effects on that larger surface are much more severe. We are all familiar with that old IC limit at 2400 Pascal, and we have to do load tests at up to 2400 Pascal. Guess what? Not one of the new panels withstand 2400 Pascal if you mount this tiny purlin right here at 450 millimeters. So those ratings have come down. So if you keep stowing your trackers at a steep angle, you are putting your panels in trouble. As a matter of fact, you are generating damage to your panel, and that's that. Okay, so I'll talk about that in a little bit. So these two things are problems that stiff trackers resolve. The third thing is value that the stiff tracker brings. If I have a very rigid tracker that does not deflect, I can stow that tracker flat, and I can increase its wind stow threshold. In the industry, everybody else with flexible trackers is decreasing that stow threshold. Because if the tracker used to be flexible, with larger cords and larger and longer trackers, it's even more flexible. The flexibility depends directly upon L, being L, the length of the free span. So if that length increased, the tracker is much more flexible, which means that you need to stow at lower wind speed. So when everybody's going lower, we are going higher. And I would like here to show a little bit the effects of these 20 meters per second. But before, let me just one more slide for number 1 here, highest stability at all tilts, just comparing, this is a traditional flexible tracker. This is how it behaves. What this thing is meaning here is that if you cross this red line, you're going to have something like in the picture down here, which we don't want to. Now, if you have a rigid tracker, this is how the curve looks like, superimposed. Okay? Like I said, at 0 degrees, it's actually the highest critical wind speed, but anywhere else, it's much higher than the red line. So that's why I can increase my stow threshold, because I'm so very far away from the from the black line, and I have no problem whatsoever. If you have a traditional flexible tracker, and now you mount larger panels, your red line actually shifts down. So your wind stow needs to shift down as well. Okay? First thing. Second thing, this is what happens to panels if you insist stowing them at steep tilts at 30 degrees and 45 degrees. If you have a traditional flexible tracker, you must stow them at steep tilts. Otherwise, your tracker flies away. That's not good because, after the windstorm, there's no assets. Not good, right? But you also must protect the modules. So people that still install traditional flexible trackers, they go and they swap panels after the windstorm. Maybe you don't see damages, as we're seeing here in the picture, which they happen, by the way. But other common damages are cell delamination, micro cracking. So after the windstorm, you go to your SCADA, and you see a bunch of strings that are performing at 80%, at 60%, 70%. Guess what? The panel has damage. It's just not visible damage, but people will go swap panels. So I don't think you want an asset to actually go swap panels after every windstorm. So we should be protecting our panels. And the only way to protect our panels, our large format panels, is to stow the tracker flat. Again, you can only stow the tracker flat if you have a rigid tracker. Otherwise, the tracker goes away, right? So that's why these rigid trackers are so important. Well, assuming that everybody understands that, now let's talk about the value. So this chart right here plots wind speed in the horizontal axis, and this is tilt, stow angle, okay? And what you can see, this is for a given site. These little numbers here are energy losses that you have comparing stowing at 0 at a very high tilt, like the top corner right here, or stowing at the steep tilt at a lower wind speed. So for this given site, we're talking about negligible losses, two losses in the 2%. So we went ahead and we did a case study here for a site in Amarillo, Texas, a 100 megawatt site, and we compared 5 different trackers. The first 2 trackers are Arctech trackers, our 1P Skyline 2 and our 2P SkySmart 2, both stow at 0 degrees. Our 1P at 22 meters per second, our 2P at 20 meters per second. And then we compared with, common places in the market. 2 trackers that stow at 30, 16 and 14 meters per second, and 1 tracker that stows at 45 at 12 meters per second. Let me tell you that these two stows right here are the most common right now with large modules. Okay, so we went ahead and we compared, we obtained for this site the wind speed distribution and the solar irradiation at the same time. And then basically, we did this analysis where we calculated the amount of hours that were beyond the wind stow threshold. For instance, if this is the wind speed distribution, and I am stowing at 22 meters per second right here, basically I am not tracking the sun in all these hours to the right of these threshold. If you compare that with tracker number C, I am losing all these hours right there. And that's what this table is showing you, right? So for instance, for this particular site in Amarillo, our Skyline 2 only lost 15 hours of tracking the sun, while tracker B lost 600 hours and tracker C lost almost 1,300 hours. Okay, so you can see that as you move left, you are in stow more and more often. Well, at some point, if you are in stow so much more often, what's the point of having a tracker? Just put fixed tilt and be done with it, right? So the intention here is actually to show everybody the effect of lowering your wind stow threshold, which all traditional trackers are doing because panels got larger. Okay, moving on. So then how did we compute that energy? Well, you are probably familiar with these curves. If you take a look at the orange curve is the energy generation of perfectly tracking day. And then the other curves are energy generation curves for fixed tilt. This green one is a fixed tilt facing east, the yellow one fixed tilt facing west, and the center one is fixed tilt facing south, okay? So what we have done in this exercise was, okay, if my tracker did not go to stow, I produce according to the orange line. This is my 100% production. If my tracker goes to stow, either at 30 or 45 degrees, I get the 30-degree line, and I use that instead, okay? Now, what happens if we stow at 22 meters per second? This is a given day. We have done this for all 365 days of the year, and then computed everything, all the energy. But just to explain the methodology here, what we have done was, okay, in this day right here, the wind speed is represented by these gray columns. And you can see that, if my threshold is up there, the wind speed has never been higher than my threshold. So I had like 100% generation, okay? So if I were to stow at 20, same thing. If I were to stow at 16 meters per second, like tracker A, I had to go to stow a little bit. So I lost that blue shaded area right there, the difference between what I generated in orange and the perfect tracking in blue. If I keep lowering the threshold, I will be in stow even more hours, which means that I will lose even more energy, right? And even more at 12. Okay? So this is what we have done for Amarillo, all 365 days of the year. And then we came up with this summary table. Okay, so Skyline, like I said, lost 15 hours, which was 0.09% of the possible energy available. And if we compare that with like a common 14 meter per second tracker that lost 600 hours, that's equivalent to 1.68% less energy. Okay, so this chart is probably a little bit more illustrative. So what you can see here is this blue curve is actually 0 degrees, and then you move on wind speed towards the right. So our Skyline 2, our 1P tracker, is stowing at 0 at 22 meters per second, right? So a tracker that's, like I said, stows at 14 and 30 degrees is losing 1.68% in Texas. If you had a tracker that were stowing at 12 meters per second and 45 degrees, you'd be losing more than 4%. So what does that even mean? Well, we put some numbers together, and again, I'm not a financial guy or anything, so I won't go through all these numbers. But I would just like to, catch your attention to, the 1.6% less energy that you produce if you are stowing at 14 meters per second at 30, when compared with our product at 22 meters per second at 0. So 1.6% more energy is equivalent to a 0.168% IRR. So many of you will understand this because you probably deal with financial models. Many other of you will say, yeah, and so what? What's 0.168%? Is that a lot? Is that much? Is that, well, we flipped the question upside down, and we said, okay, wait, if I have this tracker right here, this 14 meters per second tracker, and I need to have the same IRR, how much cheaper does that tracker need to be? So I'm on par with the IRR. And we arrived to this 1.3 cent figure. In other words, what I'm trying to say here is, if you only trigger stow at 22 meters per second and you stow at 0, when compared with the norm of 1430, you generate 1.6% more energy, And this is equivalent at an upfront cost that is 1.3 cents lower than your typical tracker. So if you want this tracker to be on par with this tracker right here, this tracker should be 1.3% cheaper. So the value we're creating here for Amarillo, Texas is 1.3 cents per watt. And 1.3 cents per watt, in the case of the United States, is about 10% of the tracker cost. So just by enabling a smarter stow strategy, we're creating value that is equivalent to 10% tracker costs. We also ran the numbers for another common tracker. And here we'll be talking about 3.3 cents, which is 25% of the tracker cost saved up front in the US. Huge. Well, not to tire you with many charts, I have like 2 more locations that are very, very important for, for trackers, where trackers are very common. We had Mecca in Saudi Arabia, and here we only generate 1.1% more if we compare with the typical 14. So that's equivalent to only 0.7. It turns out that that's the same 10% of tracker cost, because when you go do projects in Saudi Arabia, costs are much lower. EPC costs, tracker costs. So again, the value is still 10% of tracker cost up front. Now, on the other hand, you go to Chile, in the Atacama deserts, in a place called San Pedro de Atacama, where you have like the most sun in the world, say, and comparing our standard 22 meters per second with the common 1430, you generate 3.3% more every year. And this is so big. Watch. This is 2.4 cents, which in Chile means 25% of the tracker cost. Very large. Okay? So in conclusion, traditional trackers getting obsolete. They don't work that well with large format modules. Okay? If you really want to protect those large format modules, you should stow your tracker at 0 degrees. What's the only way to doing that? The tracker must be rigid. Because if it is not rigid, you will have module problems and you will not generate that much energy. Okay? So rigid trackers not only fix problems, but they also create value. And we gave the examples of the practical examples of stowing at 22 meters per second in 3 locations. And here I actually plot 14 meters per second at 30 degrees and 12 meters per second at 45. And you can see the value created up front, right? So I presented you these 2 cases here, the 10% in Mac and the 25%. I mean, if we go compare with 12 meters per second at 45, it gets like very, very large. Okay. So we published all this research in a white paper. And recently we engaged with the NV. We invited Cesar to talk after me to actually go through this methodology and run these same numbers by themselves as an independent third party, and then issue a report with the merits of this approach and the recommendations to make it even more accurate if need be. Okay? So with that said, I'm going to give it back to Tim and Cesar to go through the NV's presentation. Okay? Thank you.
Thank you very much, Pedro. Actually, if you could stay on for just 1 second before we get to Cesar, I wanted to ask one question we had put in here, and it was specifically on your slide, which used the Durst curve. So the question was, the usage of the Durst curve is only appropriate if the analysis assumes that the high tilt angle stowing tracker does not reset for an hour after the wind speed threshold is exceeded. Is that an assumption you made knowing that that's how operations in the field are? Or, could you kind of walk through your specific usage here?
Right. So, okay. So the data, well, the largest set of data that we had available here um, was in this Meritube, and the intervals came into 1 hour. Well, the data came in 1 hour intervals. Okay, so that was the best data that we were able to obtain. So we used the Nernst curve just to transform, that into 3-second gust, because codes and calculations typically are made into 3-second gust. We could not do a direct relation with what happens in the field, because several trackers use different strategies. People typically do not wait for 1 hour. They have lower thresholds. So the point here is not to be accurate to the hundredth of a percentage.
Mhm.
The point here is to present a methodology that then fed with the specific data of the tracker we are trying to evaluate could lead to an accurate megawatt hour figure. However, the comparison, the qualitative data, when we compare 22 meters per second at 0 and 14 at 30 degrees, is very, very true, because you lose energy in these magnitudes of the 1 to 2%, if not more in Chile on the 3-4%.
Mm-hmm. Awesome. I appreciate you bringing up the slide to kind of go back in your answer. That helped me to better visualize it. So thank you once again for your presentation, and I am going to turn it now over to Cesar with DNV to get into his portion of the presentation. Welcome to the webinar, Cesar. The floor is yours, unless you have anything you need of me beforehand.
Okay. Thank you very much, Tim. Thank you. Thank you to Arctech for this opportunity to collaborate. My name is Cesar Hidalgo. I'm working for DNV. I'm going to talk about tracker bankability as the main subject. And one of the topics will be what Pedro has been explaining about the stowing or tracking losses. So, yeah, I'm going next slide. So I'm going to talk, first of all, a very short introduction about my company, DNV. Then I will explain what is bankability. It's a word that many people is using all the time, but do we know what is bankable thing? So I will try to explain that. Then what are the aspects that we should review in a tracker bankability process? Because that will give us the zooming into the main aspects. So we will talk about building codes, certification, dynamic effects that Pedro has been talking about as well. So we will talk about all the items. One of them is obviously the stowing losses that in the industry at the moment is not well considered. We will talk a little bit more. And then finally, I will go through the conclusions. So DNV is an independent company. We are an engineering firm, independent. We have 4 big divisions. I'm working in the energy division, so we talk with our customers about renewable energy, wind energy, storage, solar, so that we have a lot of expertise in-house. And we spend 5% of our annual revenues in research and development. So we need to be always at the top of the industry in order to help our customers. So that's the main thing about DNV. So we cover pretty much all the phases of the projects, from the feasibility studies when you have only the terrain through the engineering and development, construction. We can help you to monitor the construction, to organize the construction of the project, and then after the project is constructed, we can help also with the operation. So we cover pretty much all the phases. So let's go to the bankability definition. It's quite difficult. It's not simple. So I try to bring here a a definition that for me is quite acceptable. Bankability means that the bank is convinced to the greatest possible extent that the cash flows are stable and the loan will be repaid. So that's an important thing here, that bankable means stable and secure cash flows. So both things is not only stable that you can have in a 3-4 years time, but also secure cash flows that you need to have it for 20 years, for the lifetime of the loan. So both things combined requires the analysis of a number of aspects. So what are the aspects that we typically review in a bankability process? One of them is the certification. We will talk about certification of PV trackers in a next slide. But for you now, what you have to understand is that certification is not enough. You will know more about this. It's important, it's crucial, because certification means that somebody has done the test for you as the user of the tracker, but it's not enough. You need more things. You need assurance about the raw material of the trackers, about the quality of the trackers. You need to be sure that your tracker has been designed for your site conditions. That's an important thing that Pedro was mentioning about wind speeds, 40 meters per second, 20 meters per second. So every site has a particular wind speed. So you need to know what is the wind speed of your site, what is the wind distribution of your site, in order to select the best design for your project. So you need to see if there is this suitability of the design for your project. Then you should not forget about the operation and maintenance of the tracker and the lifetime expectation. In the financial models, nowadays, we are talking about 20 years lifetime, 25 years lifetime, and then is moving to 30 and 35 years lifetime. So obviously, you need also to consider that when you are going to consider if the tracker is going to be bankable, because you need to know the lifetime. One thing that we typically request from the manufacturers is the management system. We look at the management system in order to understand what are the quality instructions, what are the health and safety regulation that nowadays is very important. You need to produce good trackers, but also on a healthy and safety environment. We check also the bill of materials, we check the logistics and the after-sale department. That's an important part also of the trackers manufacturers. The warranty terms is a particularly important subject for the banks. So the warranty terms need to be analyzed in detail, especially regarding the exclusions. That is typically the small letter, very long, that you need to look at. Or if it is not there, even you have to comment with the manufacturer. But you need to know the exclusions. And also, the most important thing many times is to understand what is the track record and the operational history of the tracker, because you may have all the items before almost perfect, but if the tracker has no track record or very short track record, then the bankability process can be in problems. You can have problems to get bankable, because you need an operational history with problems in order to improve and then to have a stable product in the market. Okay, so let's move to the next slide. Yeah, this is a zooming into aspects. Before I was mentioning a few of them, but you can zoom into them even more. Here I have 24 areas. Typically, we score every area, but the 24 areas can be expanded up to 70 parameters, technical parameters, in order to have a benchmarking comparison of the trackers. And as you can see, well, there are three trackers here, tracker A, B, C. It's difficult to say which one is the best one. As you can see, there is no price here, by the way. It's only technical aspects. So on the technical aspect, it depends if you are more interested, for example, in the quality certification. Probably this tracker is going to be the best one. But if you are interested in other items, you will be selecting another tracker. So the message here, when you put this benchmarking comparison, is that the best tracker is a relative term, because sometimes you will prefer one tracker because you are interested in particular items that for your company or for your organization are very important. But in other occasions, you may look for another kind of tracker. So it has to be analyzed on a case by case situation. Okay. So regarding building codes that I mentioned before, unfortunately, we don't have a building code for PV trackers. So we have to use the civil building codes that in Europe is Eurocode, in North America is ASTI. So yeah, the typical building codes used for buildings. So obviously there are some differences, and you need to know that finite elements, like here we have a joint of two sections of the torque tube, a square torque tube. You need to know the finite elements in order to give you not only if the strength of the metal joint is going to be enough, but if there is any point at the joint that will be, in danger because there is a red color where the concentration of stress is going to be too much. Okay. And then the wind tunnels. I will not talk much about wind tunnels because I like very much the videos from Pedro. So that is giving a lot of information. Basically, the aeroelastic instability that Pedro was mentioning, buffeting, vortex-induced vibration, aeroelastic deflation, all these things. Basically, what the meaning for you as a user of the tracker is that you can have a failure even if the wind speed is below the design wind speed. So even if you have, for example, a tracker that is going to stow at 20 meters per second, you can have at 12 meters per second. You can have an amplification of the loads due to the aeroelastic instability. So if your tracker is not stable, you can have this amplification of the loads. So that is why it's so important to analyze this in detail. But today in the industry I think is well known, and everybody knows what is happening. So it should be not new for the tracker manufacturer when you are asking for this information, of course. Okay. So I was mentioning before that the certification is not enough. And you may think, well, why this guy is saying that it's not enough? I have the UL 3703 certificate. I have the IEC 62817 certificate. So it's the two main certification for the tracker. So my tracker is perfect. But if you look at the small letter of every certificate, the UL certificate is more for the electrical safety. Is not considering wind and seismic conditions and nothing about the structural integrity of the tracker. So the UL is not valid for the structural calculation. And if you go to the IEC, you get almost the same. The IEC is a repetitive testing in order to detect infantility problems, so early failures situations. But the IEC 62817 is not designed, is not conceived for as for the assurance of a long time, a lifetime extension or something like that. So you need to consider that all the tests are to detect infantility problems. So no for the lifetime of the project, for the lifetime of the tracker. And I put here conditions like desertic conditions. I put here like electrical consumption that is considered in the IC standard, but yeah, is not clearly defined. So you can find differences between one tracker manufacturer and another one when you make the comparison. Okay. And then another aspect that you should consider when talking about trackers is who is going to construct your PV plant. Typically, it's going to be an EPC constructor. So the manufacturer of the tracker is not involved in the construction. So if there is a problem during the construction or during the commissioning, the EPC constructor can say, well, it's not my fault. I did all my work perfectly, and it's a design problem coming from the manufacturer. And then you are at this situation, you are in the middle. You don't know who is right, who is wrong. So for that reason, we recommend that you involve the manufacturer, you involve with this installation manuals very clearly defined in the EPC contract, and that you have a commissioning checking list by the manufacturer as well, in order to have the manufacturer with you during this particular important phase of the commissioning, and especially regarding the soil conditions, that the manufacturer is aware about the soil, the geotechnical conditions, to avoid any problem with the foundation in the future. So the soil conditions should be clearly stated in the contract, and the EPC contractor should be aware of the soil conditions, and the manufacturer, the tracker manufacturer involved as well. So that's a problem that is quite frequent today. Another issue is the 3D backtracking algorithm that is very popular now, because the PV plants are constructed in complex terrain, not flat terrain. So the movement of the trackers all at the same time is from the past. Nowadays, the trackers are moving individually in order to compensate the shadings from one tracker to another. And this is giving to you a boosting in your production that we have evaluated in a few sites, that can be 1%, for example, for the slopes, from 4 to 6%. So medium complexity or easy sites to construct, you can get up to 1%. Is not included sometimes in the capex, so you will need to pay for this additional 3D backtracking algorithm, but this is going to be worthy. It's going to be worthy, so I recommend it that you check it with your manufacturer if they can install it, if your site is complex. Okay, and then we move to the stowing energy losses. We are analyzing the woodwork that Arctech has done about this, and we are going to suggest improvements and suggestions. So but in general terms, we agree with Arctech that this particular loss has not been analyzed in deep in the industry. Many times has been neglected, and is quite significant. As Arctech has pointed out, we are not talking about a few $100s. Is quite significant. So we need to consider this in a day-to-day basis in our daily work as engineers, as consultants. We need to include the stowing energy losses, and we need also, my recommendation at the moment, without finalizing the conclusions, my recommendation will be to compare options, because it's not you can have you can neglect scenarios that are the best or the optimum for your site. So you need to consider all the scenarios for your sites. So it's in that aspect we recommend it. Sorry. So I'm going to the conclusions now. Basically, some conclusions are clear about bankability. Yeah, the industry, the PV tracker industry, sometimes is lacking of standardization. We don't have enough standardization in many aspects. So for the bankability process, typically requires the analysis of many aspects. And one of the aspects is importantly the stowing energy losses, because you may consider a particular tracker for your project that is not the optimum. And you need to have the optimum today. And you cannot go ahead with a good one. You need to get the optimum for your project. So that is why the analysis of every single kilowatt hour that you can get extra from your project is really important. And then in our experience, in DNB experience, that we have been issuing a guideline for bankability of trackers in 2018, is that in the last 4 years after submitting this guideline, there have been so many important features in the trackers that the industry has to adapt to this movement so fast that sometimes it's difficult to look at the details, like the stowing losses, for example. You are focusing on many aspects, and then you don't realize that you have one in front of you that will require more attention from your side. So in that respect, I think it's important that we have identified here in this webinar, and then you can consider for next projects that you may have in mind. And I think that's all, Tim. I can pass the floor to you. Thank you very much.
Thank you very much, Cesar. I appreciate your kind of excuse me, I appreciate your presentation, kind of elevating and showing the real world kind of financial comparisons, and providing that perspective on what Pedro already laid out for us here. So with the few minutes we have left, I want to move into a couple of audience questions, and we have quite a few audience questions. So starting with one right here, someone was asking about the cost of having 2 fixed points or drivers. Does that really still lead to lower overall costs, or how does that factor into the total financial outlook of using a rigid tracker system?
I'm assuming that question is for me, right?
Yes, sorry, I will address these questions too.
Right. That's a very good question, by the way. So I'm glad that the message is coming across. So yes, increasing the number of drives. As a matter of fact, the example that I showed on my slides had like 3 slew drives, not 2, 3 slew drives. So we moved from 1 to 3. Increases indeed the drive cost. Okay, because we used to have 1 7-inch slew drive, and now we have 3 5-inch slew drive. It's not that we multiply that cost by 3, because the slew drives have gotten smaller. Okay, but the overall drive cost has gone up. However, like I said, the whole idea is that the tracker stows at 0. If the tracker stows at 0, the pressure onto that surface is much, much lower, which means that the loads that go on to the torque tube, to the purlins, the torque tube, and the post are also lower, which enable less steel utilization. So what we expend more in drives, we save in steel. And the overall cost is actually lower, not higher, than the traditional flexible tracker.
And just to follow up on that, Pedro, if you're saving in steel, then the overall weight is lower or comparable, or what does the weight versus a traditional tracker look like?
Right. So the overall weight is lower. If you're mentioning that's the common metric of tons per megawatts, yes, we have lowered our tons per megawatt because we have less steel.
Great. So another question here for you, Pedro and Cesar. We will get to the questions for you very shortly. Was someone asking about terrain applications and wondering if rigid trackers are limited in their terrain to almost exclusively flat land, which, as we know, in project development is coming more and more uncommon. So, in the sense that there is less flat land, are these rigid trackers more limited or equally limited to traditional trackers in the kind of undulation and uneven ground they can be installed on? And if they are less so, how do you factor the necessary groundworks into a financial analysis?
Right. So, no, short answer, it is the same. So, as a matter of fact, we released our Skyline 2. Our Skyline 1, the original, was a traditional flexible tracker with one slow drive in the center and then just long half wings. Our Skyline 2 is the rigid one with 3 or 4 slow drives. And the tolerance for different slopes and terrain rugosity is the same. This is 20%. And that comes mainly given by a feature that we have in our bearing posts that allow those bearings to rotate a little bit and accommodate to that. So, in other words, or in summary, adding 2 more fixed points doesn't change the previous specification.
Appreciate it. So that makes a lot of sense that it wouldn't really have any distinct disadvantages as compared to regular trackers on uneven terrain. Okay, so first question for you. This was actually asked during your presentation. They wanted to know what does it mean to get a higher net energy gain from backtracking? And they were asking because they understood that backtracking is always a loss from suboptimal tracking.
It's always a loss. No, the backtracking is a gain because the shading losses at the first moment of the day or the last moment of the day when the trackers are more vertical, the shading losses are impacting the production. So at that moment, the backtracking is going to reduce these losses because they are not going to impact, especially I'm talking about the electrical losses. So when one PV module is shaded, then all the string is compromised. So it's not only one module, but it's all the string. So yeah, that is the 3D backtracking. Especially because every tracker is moving in order to compensate the shadings of the terrain on the following tracker. So it's not like all the trackers are moving at the same time, but every tracker has an individual algorithm in order to compensate that shadings from tracker to tracker. So the 3D backtracking is totally a gain. It's not a loss. Yeah.
Mm-hmm. Pedro, going back to you here, we had a couple of questions regarding how module level power electronics add to the overall loading and load balancing of trackers and kind of the optimal area for them to be placed on for load balancing. Just a quick bit there into how module level power electronics kind of play into the equation.
Right. I'm not sure if the question is about the interaction between module size and tracker arrangement or module arrangement on top of the trackers.
I believe it was about module arrangement on top of the trackers.
Right. So yes. So for the first time, we now have like 2 families of modules, right? What we call the 182 millimeter cell modules. Those are typically strung in 28, 29, and 30 modules per string. And now we have this family of 210 millimeter cell modules that are actually strung in 32, 35, 38, or even 40. We've done projects with 40 modules per string. So unfortunately, from the tracker perspective, we have no control whatsoever about that. And because that spec comes from the plant designer, the guy that did like the electrical design. So he optimized that those strings together with the EBOS and the inverters, and then they come to us and they say, "Oh, you know what? Now you need to supply a tracker that fits all of that." And that's very hard to do if you have a traditional flexible tracker because there are no variables for optimization. You have one slow drive in the center, and then the only thing you can do is put one module after the other. What else can you do? Now, with rigid trackers, with several fixed points, I can actually move those fixed points exactly where I need them if I have a string of 28, 30, 32, 38, 34. So I can configure the tracker so its rigidity and its performance does not vary if I have 210 cell modules or 182 cell modules, which does not happen with traditional trackers.
Great. Appreciate that. Cesar, another question for you here. This is more general on sort of the wind testing side of things. Someone was asking, to perform a valid wind stow analysis, it's critical that the wind speed data source is accurate. Has there been any work performed by DNV to validate wind-specific sources for the purpose of project-specific wind stow analysis? So I think just validating that the wind being used in testing is similar to naturally occurring wind. Just any testing of wind sources.
Yes, a very, very good question, because, well, I can differentiate if they are referring to pre-construction phase or post-construction phase. Because if it is post-construction phase, wind speed of the meteorological stations on the site that typically are part of the scope of the tracker manufacturer, they provide this in order to protect their trackers. They install meteorological stations, so the source should be those meteorological stations with anemometers, wind vanes, or all the sensors that the manufacturers they consider the best for their products. But if they are referring to the pre-construction phase, then the pre-construction phase is quite difficult, because, well, difficult, I mean, because in the wind industry there are um, capabilities to modulate, to simulate and the wind speed over a flat terrain, over a complex terrain. But typically you need a lot of calculation that for a PV plant typically is not considered. But so DMB in those cases, we are using mesoscale wind data if it is needed, and it can be it can be modulated in particular areas with high wind slopes. But yeah, if you don't have measurements like the wind energy industry, that they put met mass in the pre-construction phase, and then you get the wind data from there. Here in the PV industry, typically we don't install even pyranometers for before the construction, so they don't install anemometers for that. So you need to take sources, mesoscale data, satellite data for wind speed is the only source that you can get. But I think for the purpose of calculating this kind of stowing losses, I think as you are going to compare options, is not critical. You are going to compare one option with another, so at least the selection of the optimum option for your project is not affected by the source. It's going to be the absolute value when you have this uncertainty, and then you should consider increasing a little bit the uncertainty if you don't have a good source of wind data. Yeah.
Appreciate that answer. I've done quite a few webinars here on trackers, extreme weather, extreme wind. I've never kind of had one asked about the modeling of the wind source, so I find that pretty interesting. So we're a few minutes over on time here to make sure we had time to address questions. Again, if any of our attendees have any incredibly pressing questions, feel free to submit them to us, and we will work to get either Pedro or Cesar to answer them for you. But in the meantime, I would like to thank you both for participating in this webinar today, for providing us with those wonderful, super informative presentations. So thank you to Cesar and Pedro. And just as we had in the beginning, just before we head out today, a little bit more housekeeping. There is the latest PV Magazine news. We've got 2 featured articles here, one by Bella Peacock, one by our very own Ryan Kennedy. Natural hydrogen, how it works and why companies are interested, and Texas Solar is booming, but batteries are not included. Right there, you can see a 10% off coupon for a subscription to our print edition with code webinars10, or you can scan that nifty little QR code. It'll take you right to a subscription page. And coming up, I believe we have a header for a few more webinars here. Yes, we do. Look at that. On Thursday, the 28th of April, we have how automation can deliver sustainable solar project O&M in an uncertain environment. And then on the 3rd of May, a Tuesday, we have 7 proven ways to improve LCOE in PV and storage. New Protus inverter from Gamesa Electric. There are many more to come, as well as there have been many that we've hosted so far. You can find out about new webinars or go back and listen to one of your old favorites. Maybe it's this one, by going to www.pvmagazine.com, pv-magazine.com/webinars. There you can register, download, find recordings, anything you could possibly want to do with one of our webinars. Before we head out, I would like to ask all attendees to please take some time to fill out the survey that you will be getting. Look at, there it is. It just popped up on my screen shortly here. We really do appreciate any feedback that you give us on those surveys. It helps us to develop content better catered to the interests of you, the audience. So one more time, thank you to our presenters and thank you to our audience today. I hope you have a wonderful rest of your morning, afternoon, evening, wherever you may be, whatever time it may be. I hope it is a wonderful time for you. I've been Tim Sylvia. Thank you for attending our webinar.
Thank you. Bye.
Bye.